見ながらあとなんかアモンクラス誰かYouTuber 見ながら皿洗うときにトイレこんな好きなことがあっていいなそれでも同じサービスですよ。
All right, we're ready for the next speaker. Next up, we have James Wells, who's the interim CEO and Chief Commercial Officer at Sanctuary AI. He was very recently appointed, so we're very lucky to have him talking with us today. And Sanctuary, I think I've been writing about for a while, and I think that they realize, maybe earlier than almost anyone else, just the value of data, as we've been talking about a lot this afternoon. And so they've been having humans in the loop, collecting data for their robots for, I think, maybe longer than anyone else. And I'm very curious about how they are going to leverage that to get robots that can have like a general purpose, human level performance, as I think that they put it, which is very optimistic and ambitious. So I'm looking forward to hearing more. Let's welcome James.
Thank you. Good afternoon, everyone. My name is James Wells. As I was just introduced, and I was appointed CEO about 30 days ago. And the first thing I did as CEO is I called engineering and I said, make the robot taller. I didn't. I actually brought my kids to the lab. They hadn't been there for a while. So I was the 6th employee, and we started this company in 2018 with a very ambitious mission statement, which is to build human-like intelligence in general-purpose robots. And I remember those first sales calls where people were asking me what that actually meant. So every presentation, I always start with the same way, which is defining what that actually means. So for this crowd, this is probably fairly obvious, but our definition for intelligence is the ability to achieve goals. And I'm going to go on a risk here and try and define artificial and general intelligence, which is a system that can achieve any goal in any embodiment, in any environment. And that starts to get pretty nonsensical if you start thinking about all the combinations. So we had to constrain the mission statement to human-like intelligence, which is achieving human-like goals, which is generally what humans do in exchange for money, in a human-like embodiment, which isn't necessarily a humanoid, but it's a mobile, a bimanual, dexterous machine in any human-like environment. And of course, that speaks to the trillions of infrastructure that humans have built for ourselves to carry out work. So if we are successful in achieving our mission, we're addressing one of the largest capital flows in the world. So almost 30 to 40 trillion annually flows from employers to employees. And that is the goal of the company. And I've indicated we are located in Vancouver, Canada. Okay, there's a lot to talk about. I've got 15 minutes. I was going to focus on something that is quite unique to us, which is dexterity. So I agree with the folks at Tesla here, where half the engineering of Optimus goes into the hand. We built 9 generations of hand. We've tried to build cable-based hands, pneumatic hands, actuated in-hand hands, and the challenge we see is the industry is largely stuck in this paradigm of low power density. And so when you compare the power density of electromechanical actuation with the human hand, it's not even close. And so we started thinking about 3 years ago, how can we actually have a shot at achieving human level dexterity? And so we've been pioneering this approach using hydraulics. So I'm going to show you some oldie but goodie videos here. The early days where we showed you could get millimeter precision. So here we are peeling a bunch of labels. This is at our first deploy. And you can see some of the hydraulic cabling there. And then this is a soldering video, again, doing bimanual sub-millimeter precision, where we are soldering a wire. And so it really comes down to power density. So this is a plot where we compare the vertical power grip of hands over degrees of freedom. And what you see is as you increase the degrees of freedom, which you could argue is a proxy for capability, you lose strength, you lose power if you're doing electromechanical actuation. Except that's not true with hydraulics. So hydraulics is a pathway that we believe we can actually achieve human level dexterity. The challenge, of course, is there's a lot of engineering problems with hydraulics. So they can leak, they're generally at high pressure, there's no off-the-shelf components, and they're huge and don't actually fit into the humanoid form factor, and very low flow resolution, which means it can't really talk effectively to the other parts of the robot. So the big breakthrough we've had this past year is to miniaturize the valve and actuators to enable hydraulic actuation in a tight form factor in a humanoid. So here you see our valves and how we can gang them together to actually go in the forearm. So for every degree of freedom, you need one of these valves. And it's pretty amazing what the results have been. So the pressure in the system is no more than the pressure in a hydraulic bike brake. It's very low power. We actually just hit a milestone where we did 2 billion cycles on the actuator without any leakage or failure. And this system's been running on our robot for about 20 months, and we've seen about 1 million cycles on the valves with, again, no leakage or failure. And we compared it to off-the-shelf, which is a little unfair because off-the-shelf hydraulic valves would never make sense in this particular application, but we drove down the cost and increased the flow rate. Okay. I'm going to show a couple videos here. Turn my phone off. That's a good idea. I was the CEO of another humanoid company. Oh, sorry. Come on, Betsy. Okay, we're gonna skip that one. Every hand video needs an egg video. So here we're showing that we can crush an egg, but also not crush an egg, because you have force estimation within the hydraulic fingers. This is a video we just released. Oh, come on, let's go. There we go. Just demonstrating in-hand manipulation. This is a 19 DOF system, almost ubiquitous across a lot of the customers we interact with. They are looking for systems that can chaotically or blindly pick a part, reorient that part for then an insertion task. And so in-hand reorientation is a big focus of what we're doing. This is a 4 DOF thumb that's adjusting wrench. And this is a video we just released today where what I was saying, you have to pick an object in one grasp pipe, reorient it, and then insert it back into a fixture. Okay, 19 DOFs isn't enough. So touch is a really important aspect, and about 18 months ago we partnered with one of the leading haptics experts in the world, and this is hot off the press here. So this is our next generation finger. It's a 3 DOF finger with a white haptic sensor on there. When I was playing this video, my son walked in and said, "I thought you were building humanoids. Why are you building a brontosaurus?" I was like, yeah, fair point. Kind of looks like that. Okay, so that's the next gen finger. Now I'm going to show you some tactile feedback here. Very sensitive. So it's about 5 millinewtons in sensitivity. There's 7 air pockets, and it's extremely responsive to just a paintbrush. It's like the brontosaurus is smelling something. It's like, oh, I don't want that. Stay away. Okay, we'll stop torturing it. And this is something you can try and do at home and see how well you do. So when it touches the domino, it stops. Okay, the other defining feature of Sanctuary is our intellectual property portfolio. So we got going in 2018 with some very visionary founders and basically mapped out a 10-year road of how we would actually achieve the goal, and started filing IP in each of those major activity streams. And so sort of as a side effect, we find ourselves here being ranked quite favorably amongst the community. So in terms of patent volume, we have the most patents out of any startup, but we're right up there with some of the name brands in the category of general purpose robot or dexterous manipulation. It's pretty cool to see we're ahead of NVIDIA and Microsoft in this area. So the key categories is hardware, software for dexterous manipulation, how you can collect data and train, how you can evaluate and deploy models, and then managing fleets. And so some of the key patent families are around using LLMs and robotic control, how you use visual servoing or haptic servoing, model training with teleop. We've been doing teleop for since 2018 and patented a lot of the techniques there. And then, as I mentioned before, we build all kinds of hands and have continued to innovate and patent all kinds of those actuation mechanisms. On the AI side, I'm not going to show any demos, but I just want to bring focus to a really big challenge that people have been talking about, and it's how we get the last 20% of policy performance. So all this imitation learning, behavioral cloning gets you to policy performance of 80 to 85%, but the real trick here to unlock this industrial end-to-end models is to get to that 95, 96, 99%. And so we've been experimenting quite a bit with blending that with reinforcement learning and online RL. And I'm not sure if you can see this, but here's just a data point on a very complex pick task where we've managed to use RL to kind of achieve some of those I'd say commercially relevant performance levels. And that's where our AI is really focused on, is how can we fine tune it to get to a level where we can actually start to get bankable POs. So the mission still remains. When I take a step back and sort of evaluate the differentiated value that Sanctuary brings to the table, we've got this hydraulic hand technology, we've got this AI platform and this IP portfolio, and we're opening up to different partners to utilize our hands. We're opening up some of our intellectual property and actuator technology to share with the community. It's applicable not just on humanoids, but also non-humanoids, all in service of kind of feeding the business needs of the enterprise. So just to quickly summarize, we're about 150 people. We're based in Vancouver. We're going to hit 4 million revenue this year. We've got 3 go-to-market customers and partnered with folks like Magna, NVIDIA, and Microsoft. Okay, there we go. Time for questions? Yeah? Yes, sir.
You said 2 billion sizes. Was it for a single human actuator?
Yeah. It's a piezoelectric actuator that you can vibrate quite rapidly, so that's how we could get the cycles up so big. Yeah.
Share with us some lessons learned from your work with Ag.
Yeah, so Magna's been an investor for almost 3 years now. And Magna's interesting because they're Canadian, and the Canadian government cares about scaling the automotive industry. And so when you look at some of our components and components in EVs, it's kind of a natural partnership. And so if you're following the automotive industry, they're struggling a little bit. There's lots of layoffs. And so we are that new product opportunity for them. But they're still a car company, right? So the interesting part here is I'm like, look, just do what Tesla's doing and run the same program. But they're not orchestrated, or I'd say have an innovation mindset that's comparable to what we're seeing at Tesla. So a lot of these folks are really trying to, at least the C-suite and the senior leaders are really trying to pivot and grow the businesses in new growth areas. But it's a 60-year-old legacy automotive group. So there's definitely a spectrum of automotive manufacturers and suppliers that respond differently. But they're as much a scaling partner as a capital enabler as well to access some Canadian dollar government. Yeah. At the back.
How much of the revenue is global today?
Sorry, one more time.
What percentage of the revenue is based on deployments?
Is based on deployments. So it's all proof of concept data or pilot capital. So we've got a graduated way we run a process that we run clients through. And the product scaling revenue comes when you hit commercial KPIs. And that's generally a function of speed, quality, and availability. And I'd say other than agility, a lot of folks aren't quite there yet. And that's kind of the metrics we're working towards. But it's all, I'd say, pre-commercial revenue. Okay, hearing none. Keep your eyes peeled for that tall robot.
Next up, we'll be hearing from Devantro. The title of that presentation is 4 Weeks at Home with a Humanoid, which sounds to me both like a futuristic fantasy and also a potential nightmare. But I think that if I was elderly and living alone, my perspective on that might be a lot different, and I think that's what Raphael is going to talk about. And I also just wanted to mention that Raphael used to work on the Roboid project for many years. My picture in the app for this conference is me hugging Roboid. And don't tell anyone, but that was taken in 2013, and that is still my favorite picture of me with a robot of all time, and I take a lot of pictures with robots, so that should tell you how big a fan I am of that robot. And hopefully he'll maybe show a couple pictures of Roboid, so I can live a little bit of nostalgia there. But please welcome Raphael.
Good. Yes. So I tried to make it entertaining, given this is one of the last talks today. Good. So just so you know, this is Roboid in 2013. It's a fully musculoskeletal humanoid robot. I adopted it. I was a part of the team that originally designed it, but it wasn't sort of mine. But then I adopted it, took it over. We built the second generation humanoid, also musculoskeletal. You can now visit it in the German Museum. And in 2020, we built the third generation of musculoskeletal humanoid. And I think what this shows is we spent a lot of time doing very painful things. And we're not afraid of doing these things but also there's use cases for this. So this is one collaboration we're doing for many years now. This is with the University of Oxford. They're using our robots to train tendon in shoulders in the hope of one day being able to implant them back into humans. And they're using musculoskeletal humanoids because this creates realistic strains on their shoulder tendon pieces. So that's one of the very few use cases we found for this technology, and sort of thanks to the pandemic, and also thanks to showing our robot at fairs over many years, and I think Roboid is about the most hugged robot out there. We really understand what it means to be close in physical contact to a robot, and so that's one of the reasons we pivoted over to care and abandoned the musculoskeletal approach, at least for now, because also everyone keeps talking about having humanoids in homes, and you probably know this Goldman Sachs report says, well, there's not going to be any humanoids, even in the blue sky scenario, before 2027. So we thought, hold my beer, let's see what we can do quicker. So this is some impressions. Our humanoids in private homes. So these are all private living homes. It's where people privately live. And we left the robot with them. So there were no engineers present. Of course, they were outside of the flat and could react at any time, but they were staying with the robot alone. And so I think we need to correct that report. There's no human homes at least before 2024. So let's talk about what it took to get into homes as fast as we can and why we did this. So first, robots are dangerous, right? Especially humanoids. So the easiest way of making it safe is making it weak. So our robot cannot lift more than 1.5 kilograms. So these water bottles are challenging already, but that's totally okay if you really look deeper into the use case. It's actually not necessary to create a viable business model for lifting more than 1.5 kilograms. Then we built a soft skin around it. So this robot, you can hug it, it can bump into stuff. It's very soft and there's nowhere you can basically squish yourself. So it's safe to interact, which is really important. We used a lot of off-the-shelf parts. Basically, we bought arms that are already existing and fitted it into our system. And we had trusted partners that helped us with the paperwork. So this was a study. This was conducted together with Charité Berlin, which is one of the most renowned German university hospitals. They were sort of helping us through the paperwork, through the ethical application, making sure, of course, we had like study insurance and so on. So this was a safe and controlled environment in the sense that everything was made sure we're not going to hurt anyone. And of course, you're not going to do anything autonomous with humanoids in homes, not with a 50-kilogram robot. So it's all one-to-one teleoperation. So this is Robody, that's the system we built. You can clothe it however you want, so this is a choice, and we also gave this choice to every person who went into HomeWeb, and interestingly, every person choose a different dress. We had 4 dresses, we had 4 pilots, and we had used them all. And I think one of the things we're seeing so much, we're seeing all these humanoids, and if you're honest, we are all teleoperating our humanoids. So why not make it obvious? Why not actually use the fact that there is a person on the other side and show that person and make it not just a robot, but make it a communication tool and a communications instrument. So we added a face people can trust. And this was the #1 thing in the analysis afterwards. Everyone kept saying the face was absolutely crucially important. And yes, it looks absolutely creepy. And I'm sorry, it's my face and I have a resting bitch face, so I'm sorry. We will be using different faces in the future, working, making it nicer, but actually, it is still a very, very important feature to be done. So please meet our test users, our test customers. They're all well in their 80s and 90s. I think the oldest one was 95, so really old and well-lived people, all very, very charming. They were all living alone, so they had relatives visiting sometimes, but they were not, they were living alone in their home. This was a requirement. They were all in need of care, and none of them was actually afraid of robots. They really liked it. They really loved having that robot in there, and I'm going to show some impressions from that. And they loved the face. So we now have the challenge, we need to upgrade the face because relatives are like, ugh, but the elderly actually love it the way it is. So our core user group doesn't have a problem with that. And, come on. Well, stuck. No. So quickly, what was the study setup that we did? So with 4 elderlies, 1 week each, they're all living alone, they all are in need of care. So they have care services coming once a day, each of them at least. They're all cognitively sound because they needed to be able to agree to be part of that study and understand the risks and also understand what they're agreeing to, because it's a multi-day complex pilot. We also did tests with people that have dementia but outside of the study. Basically, we came in on Monday morning, we set up the robot in their home, and then we left. So from Monday afternoon to Friday lunchtime, they were alone with the robot. We turned it off overnight because we didn't want to do 24/7 telepresence, but the robot stayed in their homes. And we were talking with them, like, how was it having this robot at night? Weren't it scary? Because when one of our test users, she walked past it every time she went from her home from her bedroom to the toilet. And she was like, no, I knew it's there. So for me, this was really comforting. I kind of knew someone is there for me. So it was not what we expected. We only went in when there was trouble, and on average, this was about once a day. And the rest, I said, Robody stayed overnight. But let's talk about what we learned, because I think a lot of those learnings are really important for bringing humanoid robots into homes. So first, homes are full of stuff. Especially homes of elderly people. They're really narrow. So this is an assisted care home. It's her private flat, but it's tiny. It's less than 20 square meters. And because of that, you keep bumping into stuff. So it's really important to have a robot where it's okay and safe for it to bump into stuff. And we did so a lot. And one of the first things we fixed, because the gripper wasn't padded, and we left a scratch in the fridge of the first test user. For the first thing is we padded our gripper as well, because it's just unavoidable, because they have so much things in there, and they have carpets, and you need to glue them to the floor, otherwise they get stuck in the wheels. Like here on the left side, these drawers, they have these really annoying little knobs. So what we put is cable ties, and with the cable tie it's actually very easy to open it. But that's something you can do in an elderly context. Like, who of you would accept this sort of from their household robot? Probably not a lot of people. But in the elderly context, that's fine, because this really means a difference from being able to stay at home. You have to go into a care home or get a living caregiver, and really being dependent on a person you live with 24/7. It's also quite important, like stuff is never really on a good location. Like getting things out of fridges is really hard. Opening fridges it's a really annoying thing because fridges, they have this vacuum and you need to work against that vacuum and then it suddenly opens. So basically the robot will quickly move. We also spilled yogurt and our robot doesn't get to the floor, so we had to get in, and this was one of the interventions. We had to clean the yogurt from the floor. And I think what's really important is we know as roboticists every home is different, but every home is different. It's such a huge variance. Everything is not just a different location, but it's different height, different aspects. You need to know where what is. We really also struggled with very simple differences between homes. And I think when we think about generalization of robot learning models, you are really looking for something really unstructured and very different between those. These are just German homes. And I think one of the most important aspects is we always see these videos where robotic companies show like a robot can iron now, and we see this iron in motion, and that's the task. So we've been doing laundry as one of the things we've been doing. So loading the washing machine and hanging up the clothes after they were washed. But we can actually not do that task because we could not set up the place to hang up the clothes. And one thing is, if you look at a lot of those tasks in homes, what's really missing is you need to do the task from the very, very start to the very end. And for ironing, for example, that includes setting up that ironing board, plugging in the iron, you have heat. It's a very, very complex thing to do. And this is so easily underestimated because we tend to just prepare things in our labs. And in a home, you can't do it because everything you need to prepare means someone needs to do that for the robot. So if you go into homes, your new nemesis are going to be containers that are really hard to open. And a lot of small things that you don't expect. One thing is also, like elderlies, they really need, they often are too frail to walk on their own. And one way of tackling this problem is actually not making the robot robust enough so someone can lean on the robot, but by having the robot use tools that are available, like a walking aid in a home, to make this possible. And this way we have a very easy separation. We can actually help someone go to the toilet that's no longer fit to walk on their own without them actually endangering themselves because they're leaning onto the robot. Users absolutely love these active tasks. And if you make it playful, they become really, really active and invested into these things. Actually, one test user, she's a diabetic, and the day where we did most of these interactions with her, she didn't need insulin in the evening. She was so active with us, she completely forgot. I mean, she was tired in the evening, but she totally forgot that she's active. And it's not just that, but they also start to help the robot. You're seeing this here, like the robot drops the stone sort of somewhere in between, and she actually then moves it to where it's supposed to go, and then takes the board to her, and then it takes a long time to think about her next move. And that's perfect because after the third move, I realized I can use the time to grab the next stone. So actually this game was not at all slower than as it would have been if you were playing this real life. So this way of the users actually helping a robot is really important in elder care because it means that people are more active, and it's really making it hard in any other kind of use case, because if you have a robot that's supposed to make a coffee in the morning and you have to help it every time, you don't want that robot, right? But for elder care, having success rates in, I don't know, 50% is actually fine because the user becomes more active. And they absolutely love it. So this is, I'm not sure if you have sound. I mean, she speaks German, so. Do we have sound?
Da Erwähnung stand gar nicht am Anfang, aber das ist nicht der Fall.
Yeah, so she made these socks for him and he's now wearing those socks. And it was beautiful. Like she really, and the thing is, she can't actually use a microwave. She doesn't know how it works anymore. Like her son explained it to her 10 times, she still can't do it. Interacting with a robot was zero problem because for her it just works like a human. And they really sort of start to love it. They start to build a relationship with the operator through the robot, and we get quotes like, actually it felt like you could just step out of the robot anytime. It's like you're here with me and you're just wearing a weird suit. And that's exactly sort of the kind of interaction we wanted to build. Dementia is not a limitation. We've interacted with lots of people with dementia. See, she has a very, very advanced dementia, but she really wanted to hug the robot, so of course that's what we did. This is the operator perspective. So that's how I saw it. After that she said things, "I love you," and I was like, "No, I'm married." But it was very nice, and we could really interact and talk with them, and it works. And also the caregivers actually love it.
Also uns haben sie komplett begeistert. Also unser gesamtes Team ist total begeistert. Ja, und es hat richtig Spaß gemacht, damit alle zu lösen. Also vielen Dank auch nochmal.
Ja, danke Ihnen, es ist für uns was.
If you can't convince the caregivers, you're not going to deploy into care. They need to be on board, they need to love the system. Otherwise, the first thing that happens is you're going to end up in a corner, it's not going to happen. So we're really happy that they're actually allowing this. One other thing is they're actually not spending a lot of time with that system. So we had to trigger all the interactions. They could use it, like we were listening in 24/7, they could just call it at any point. They didn't do that, although we trained it with them multiple times. So they're not looking for constant entertainment. They're really just looking for safety, for ensuring someone is with them in their homes. And we did about 2.5 hours of interaction every day, and this was exhausting already. So we think around 1.5 hours of teleoperation is necessary to keep a person with dementia in their home throughout the day. And that's actually really cool. I like a robot that's not doing much, and it only moves 1.5 hours a day. So this low utilization is actually really useful for us. And one thing we learned is trust builds actually too fast. So after the first day, they get so comfortable with the system that they do things that we told them they shouldn't do, and they still do it. Like I was in the fridge trying to get out cheese and so on, and I suddenly see an arm coming through, her grabbing something from the fridge, and the arm going away while I was working in the fridge. I was like, how? You can't, like I was moving, so I mean, as soon as I saw it, I stopped moving the robot. But for her, she just didn't see a risk anymore. And this piece of cake, you see it's cut really on a really steep angle, and that's because we used a knife to cut it. And despite me telling her, please stay away from me doing this cut, she was like, no, let's do it. I didn't want to do it, but she was really insistent on having that. And I think that's really one of those things, like we need to be super careful when we build systems for elderlies, that we take safety serious, because they will start to trust it immediately and they will think this is safe even when it potentially is not. This would all not have been possible without our amazing partners. So Charité is Germany's most renowned university hospital. Agustinum is a leading German premium care provider. Ayatanda is Germany's largest private home care provider. And Diakonie-Zentrum is sort of a very innovative but smaller, vertically integrated care provider. Also been supported by the German Ministry of Science and Education. And I think we have a really unique approach to make humanoids work in homes. So this works as a business with 100% teleoperation. We don't need to become autonomous. So this is a great data collection approach, because actually our users are paying us to collect that data over time. But we don't, once we start automating this, we don't actually need a 100% success rate or a 99% success rate. For us, because we always have a teleoperator as well, a 50% success rate already reduces our costs a lot. So I think to tackle the care crisis and have a meaningful impact, we need and want to build 150,000 systems of this live by 2029. We're currently raising a pre-seed round. If you're interested, please talk to me. And with that, thank you so much, and if there's questions, please.
We have time for one or two very quick questions.
Hi, thank you. I have a question. Do you think that the users would enjoy maybe less interaction?
Hi, thank you. Do you think that the users would enjoy less the interaction if they knew it was autonomous rather than a human behind the robot?
So this was the unified feedback. Everyone's like, it was so important there's a human on the other side. That being said, from other companies in the field, I don't think it's necessarily true. But it's what they're saying. Like they say it's really important. But I think we can get quite far with LLMs. And the question then is whether we want to.
Hi, two questions. First of all, did you get any comments about the height of the robot and whether in a production environment you would make it shorter or more human scale? And then the second question is there data that exists based on having actual caregivers about potential healthcare savings or anything like that that may make this model even more amenable?
Yes, so the height is a really interesting question. So we were quite lucky with the height because the comment was, we asked them if they were taller and lower, and they were like, no, it's actually kind of convenient so that they don't have to look too much up when they're sitting, because they're sitting a lot. So I think the height at this roughly 160 with a head, that was pretty well done from our side. Of course, it also depends a bit on the operator. If the operator is a lot taller, it's a bit weird that you're suddenly less tall, and so on. But in general, it was not a huge issue for them. Nobody was like, can you please make it a lot smaller? That being said, of course, we want it to be a bit smaller because it's really tight spaces, and the tighter we can make, the better that is. In terms of data, like the model we're building allows a home care service to turn these customers into profitable customers again. So typically they become unprofitable because they have to visit them multiple times a day. And then they become too ill, so they have to go to a care home or an assisted care situation. And with us, we can actually help them. They can put a robot there. We take all the tasks for which they normally would have to go again. And then they only come once a day for this typical medical care tasks. And these we can't do with the robot. We can't do anything like strong physical interaction, but it's also not necessary because all those tasks are rare. So they happen at most once a day. And we take all the others like managing pills, managing drinking, so they drink enough, making sure they're active and move throughout the day. So that's the things we can do.
All right, thank you so much.
Thank you.
Next up we have Burkhard Birken, who is the CTO of Hexagon. Burkhard has been working on digital reality and robotics for over 20 years, and Hexagon is exploring how digital twins and spatial AI will intersect to catalyze the adoption of humanoid robots. And I'm excited to learn a lot more about this, and I hope you are too, so please welcome Burkhard.
Thank you very much for the introduction. Welcome everyone. I'm Burkhard Birken, I'm the Chief Technology Officer of Hexagon, and today we are going to talk about the power of precise digital twins for humanoid robots and why we have the technology required to make the world work better and the ability to know before we act, and we simply call it the age of autonomy. So the vision for humanoid robots is that they will accelerate innovation, that they will automate repetitive tasks, that they will help us overcome labor shortages, and that they will eliminate waste, and this in terms of wasted resources and wasted time. So advancement in AI and simulation and reinforcement learning are unlocking the potential of these robotic systems, but we think we need to go further. So we need to use precision to unlock actually the spatial intelligence, and we need to create, as you see it here, digital twins that allow robots to anticipate and learn even better and faster. And it starts with data and an ecosystem to build the most precise digital twin possible. And building these digital twins at any scale, as you see here, and I go a little bit more in depth throughout this talk. And it's about giving robots and then AI access to accurate, up-to-date industry insights. And when we do this, we will empower humanoid robots to navigate complex environments and accomplish complex tasks. As I said, it all starts with data, but data are just symbols, mostly numbers. We make them more machine readable, it's zeros and so on, and we create vast amount of data. Researched a bit, by 2025 we will have created, copied, recorded, and consumed 181 zettabytes. And I had to look it up. 1 zettabyte represents 1 billion terabytes. Where each of us creates an average of 102 megabytes per minute. So our data volumes are growing by 23% every year. But as you see, data is not very useful on its own, and so we're getting into the topic. What you see already here is a point cloud generated by one of our Hexagon devices. It's a Leica scanner, it's an RTC 360. However, it looks already a lot like information, but we need to dig a little bit deeper. And even the information that you have contained in this point cloud is enough. So we need to transform the information into knowledge and gain a deeper understanding of a problem or a situation. As you see here, the point cloud is already segmented in various parts. And only at this point, we have a basis for insights and the opportunity to get a complete 360-degree view so that we can make the right decisions at the right time. But we would like to go even further, though we connect insights back into the world to create impact, to really make a difference. And that applies to all the industries that we work for, whether it's for manufacturing, whether it's for construction, whether it's for process industry or others. There are many reasons why projects are delayed, cost overrun occur, and problems occur. And let us use these insights to make a long-term impact and overcome these problems while we navigating and reasoning the robot. So we are in the age of autonomy, an age where innovation accelerates in unprecedented speed, as we see here. And why are digital twins so important to humanoid robots? And what does the ecosystem built around look like? And this is a blueprint on how we go about these things. You have the real world, you have a lot of sensors, and then you create a digital twin. And then you apply AI to the data, you do spatial computing, you use it to train it and get greater robotic performance, and then you basically deploy it back into reality. So this becomes a flywheel, this becomes a feedback loop. And we're doing this since quite a long time. As Hexagon and all the vital industries. Some key figures, what we do, our public safety technology protects over 1 billion people. Construction technology that is around the digital twins is active on over 350,000 construction sites, and it's used in over 90% of the airplanes. And I could go on and on and on in these 28 industries where we are. So we bring a long history of industry experience and innovation to the robotics field. I showed you the blueprint, but to form the ecosystems we need exactly 3 things. To make a digital twin, to generate insights from the digital twin, and to activate the digital twin back into the real world. So how do we make digital twins? And it's a lot about the reality capture sensors that provide the most accurate perception and data generation available today. Today, basically, these sensors that they fuse various capture methods, it's imaging, it's LiDAR, it's structured light, is radar technology, and is from photogrammetry. And these technologies have been there for decades to accurately map the world and objects across every major industry. How does it look like? Let's begin with industrial metrology, where we measure objects on the manufacturing shop floor, whether it's large volume metrology with laser tracker controlled handheld scanning, or robotic scanning using large gantry machines, as you see here in the video for the flushing gaps. And if we go bigger scale, and if our robots want to go bigger scale, then entire cities and countries are mapped using car-based mobile mapping system. And as you here see, airborne sensors, then sensors that fly with planes. So I showed you at the beginning, the start is a point cloud, and these point clouds are processed into meshes. And the imaging sensors that normally in our scanners are on board then generate the textures and the coloring. So as you see it here in this corridor, the photorealistic 3D meshes are the results. And this does not only work in very small scales like indoors, this also works in any scale. What we have seen indoors also working with the same methodology in a city like New York or Munich, as you see here, so fusing the terrestrial and the airborne 3D reconstructions together, we call it super mesh. And this is an ideal background where basically our robots can autonomously navigate and perceive the environments. But we can do this reality capture not only manually by human interaction, we can also do it with robots. Let's talk about robotics and reality capture. Robots and precision sensors go together very well. So we make robots carry precision sensors to capture reality and make therefore digital twins. They connect the digital twins via platforms and automate repetitive tasks. And there are few aspects that all our autonomous systems have in common. We use computing at the edge. So basically the results is at the machine, at the sensor. We use autonomy through robotic capabilities, and we connect the digital twin to reality. And these robotic reality capture systems are embodiment of AI. So let's talk about robotic ecosystems. That's robotic platforms that navigate and scan spaces without human intervention, and sensors adapt to the environment by continuously capturing reality, and artificial intelligence-based software connects directly to our autonomous sensors and processes that these data sensors create in real time. So combine these technology, create a complete autonomous system, complete autonomous workflow, from data capture to creation of deliverables, insights, and as I showed before, experiences. And such a systems that we probably, for the first time in 2021, put on a Boston Dynamics spot. We call it BAK ARC. BAK is our reality capture line, and ARC stands for Autonomous Reality Capture. It revolutionized in 2021 the way that we captured and navigate in 3D spaces autonomously. And as a module, it can be integrated with many different robotic platforms for very different applications. And then throughout 2021 and 22, we gave the BAKR a set of wings, and we invented a completely new flying systems from ground up. We called it the BAK to Fly. Was the world's first autonomous flying laser scanner, a system that won the Time Innovation Award in 2022. And what makes it autonomous is that it enables users to capture complex buildings, as you see here, and structures completely autonomous from facades to roofs, bringing reality capture to previously inaccessible spaces. And as an autonomous system, the BAK to Fly creates its own scan paths and flies around structures and while capturing reality in 3D. And after a successful mission, as you see it here, it returns home safely. So we have created now a digital twin, and now it's the time to generate insights with the application of AI. And we're doing it in Hexagon in 6 platforms that are geared towards specific industries to have their own domain knowledge representing in there. And these platforms, they connect people to meaningful data, and they foster also the collaboration in the industries where we are. For example, probably the one that is most relevant for the robotics industry is called HXDR, Hexagon Digital Reality, which makes sense of the data and create insights that later on also robots can use by training in this environment. So basically, you train the robot before you deploy the robot, and when the robot comes into a scene, we already know the scene. And this is an example we did in 2023 jointly together with NVIDIA. We created a digital twin and used it to simulate and optimize the manufacturing process, and then bringing, for example, from the digital twin, from various processes that you run across the digital twin into Omniverse and then back into reality. So all our platforms enable to innovate quickly and provide our customers with valuable new function, and this is the way we guarantee that our global R&D teams can leverage the best domain expertise to provide AI-powered digital twins, which comes in all of shades and colors in terms of visualization. And this is basically before you enter with a robot, with a humanoid robot, this scene. This is already the training ground, so the environment's already known. Now let's talk about AI. Where is the state of technology in this geospatial AI that we are using here, and what is available today, and how it works in this industrial application, which is probably a little bit different than the large language models or the generative AI. In which areas is this possible and already released into products and platforms? And we have done it quite early on. So for us as a company, having image sensors, having LiDARs, it was already a topic in products in 2012. And when deep learning arrived around about 2014, we developed already classifiers of identified objects in terabytes of 3D point clouds. And our initial experiments with generative AI started around 2018, and when 2022 the breakthrough came, of course we were quite nicely positioned. And we have already incorporated our AI capabilities, as you see it here, in these platforms that I was showing before, into multiple products that are actually active on the market today. And we're working now with strong acceleration with our partners NVIDIA, Microsoft, and AWS. What can these platforms do in terms of AI classification and segmentation of point clouds? Extremely important for everything reasoning. AI-based creation of BIM models. This is building information models. Their comparison with real-life measurements about construction process, collision conflicts you might have, and then dimensional deviations. And we're not only doing it for 3D data and reconstruction that was captured with LiDAR sensors or imaging sensors. We can also do it with radar sensors. So you see a radargram of what is underground with a ground penetrating radar in this little picture, and then basically you generate then the pipes with this. Or the next step where we're currently working on is taking whole digital twins and generating them directly using AI from videogrammetry. Maybe it's a run through with a GoPro camera, and then building models in there that are later then on used for training purposes. So let's take a look together how these AI-powered digital twins come to life. Let's first talk about simulation, and you're very familiar with robotic simulation. So I would like to show you an example that we're doing in the automotive industry. So basically, simulation here streamlines and enhances the automotive design process and enables you basically to all the precise insights into fluid dynamics and aerodynamics. I think it's not a secret that we are partnering with Red Bull Racing and the Formula One and many others, automotives here. And these technologies allow manufacturers to test, refine automobile performance, reducing drag and improving the fuel efficiency. And what works also with automotives also works in terms of wind simulation. It's again computational fluid dynamic simulation that we use then based on digital twins, and digital twins are then used to represent, analyze, and visualize the interaction and influences in urban areas. And of course, that's the point. Digital twins and simulations are used to improve robotic performance. For example, this is our factory where we basically calibrate these sensors. You saw the point cloud, you saw the meshes, and then basically we generate models out of it, and then basically for any robot coming into this factory for us, we deploy or train the robot before deployment there. As you see, for example, with these two Boston Dynamics Sport robots carrying the reality capture sensors. So robots capture the reality. The point cloud they create makes the precise foundation. We talk about millimeter precision for our training models. Built upon with the AI segmentation and the photorealistic digital twins. And then we simulate the robotic reality capture and spatial navigation. And this is how we think you can deliver the most accurate form for your robotics performance. And I think this is key to unlock spatial intelligence, enabling humanoids work jointly, because you know the environment and you perceive what is moving around with safety and precision, and humanoids then are connected to these platforms. So basically you can play and deploy the insights from these platforms to the humanoids, and the simulation created with large reality models is where spatial intelligence unlocks for real world results. And this will, what we think in the future, also allow humanoids to better understand the world around them and take on increasingly complex tasks. So when we go back to my beginning from data to impact, I wanted to show you how our technologies fully connect digital twins and give humanoids access to insights that will accelerate their performance across all the industries, because we have, in a large number of industries, we have actually the experience in building this and building a perfect sandbox before they be deployed into this industries. So with that, I would like to welcome you to the age of autonomy, and I thank you very much for your attention. Thank you so much.
Our next and second to last speaker. So many of our speakers today have acknowledged that safety really has to be a top priority when we are deploying humanoid robots into the world, especially into more complex environments, and especially then be interacting with people or working close to people. And this is something that Synapticon has a lot of expertise in. And CEO Nikolai will be able to talk about making humanoid robots that are intrinsically safe, which is a very high bar for safety. And I think if we can hit that, it'll get us a lot closer to having humanoid robotics ubiquitous out in the world. So I'm looking forward to see how we get there. Thank you.
So, third European in a row. They put us to the end of the event, I realize. Let me ask you a couple of questions. It's nearly the last talk, so who's still attentive? Yeah, great, amazing. Second question, who knows my company Synapticon here in the room? That's not too bad. So we're a German-based company, but we feel pretty native to the Silicon Valley actually, with I think it was 5 groups at Stanford University being early adopters back in 2013, and half of the startups that were acquired by Google then just a year later. Mostly ending up in the Everyday Robots project that we also accompanied for 8 years, and working close with Open Source Robotics Foundation to help creating the foundation of ROS2 actually back then. Who don't know us, take a look. We make it very easy to develop advanced and high-performance robots and to make them safe. And about that I'll talk a little bit today. Last question for the start of this presentation. What do these things have in common? Any idea? So they can all kill people, actually. For a couple of them it's pretty obvious, for maybe not all of them, but they actually can. For nearly all of them, functional safety technology is there to solve that problem as much as possible, but it isn't solved for humanoids. So let's take a look at state-of-the-art functional safety in industrial robot applications first. So mobile robots. We're using safety-rated LiDARs and other sensors to basically detect obstacles and dynamic obstacles, that means also humans, without classifying them, to slow down and stop the robot. For this, besides the safety-rated sensors, we need safety-rated drives and safety-rated position encoders to have a fully safety-rated system that always can be relied on. For example, for situations like this, where it could become potentially very dangerous for the human or even lethal. Now for robotic arms, so industrial robot arms, the most advanced implementation in collaborative robots that can feature a suite of safety functions to be able to interact with humans and be safe for humans. So these are the 4 safety feature suites, so to say, that are defined by 15066 that now is being integrated to the main industrial robot norm. That not only includes stopping the robot safely, but also to slow it down, to have a safe working envelope, safely interact with the robot. So a stack of safety features are required, like safely monitoring the speed, safely monitoring force, limiting the motion envelope of the robot, and so on and so forth. But how is this actually implemented? So what does it mean for a system to be safe? So first of all, and that is a common misconception of functional safety technology, we're not making the actual control system safe. So the non-safe system remains non-safe. So the robot controller remains the robot controller. The AI that drives the robot, that controls the robot, remains the same non-safe AI after all. That usually runs on just a single computer without redundancies and so on. For example, that could be a servo drive controlling a motor and a brake in an axis, in one degree of freedom of the robot. And in order to stop this, we need to have some safety circuitry to safely disengage the motor and to safely pull the brake. So safe torque off and safe brake control being the most basic functions here. Most easy case is to trigger this with an emergency off button, the most primitive form. Now, when it comes to safely monitor the motion, we need an instance for that. So we need to have a safety monitoring system that does exactly that. It's watching the non-safe system, what it does, and make sure when it goes out of the envelope of speed, position, or torque, we can trigger, for example, a stop. We also need a safety-rated sensor for that, or redundancy in the sensor system. And redundancy also in the compute that the safety monitoring system is using in order to reach safety integrity levels above 2 or going up to 3. I've been mentioning stopping the axis. Why do we want to do this? Because the universal safe state of an industrial robot, at least, is a stopped robot. So within functional safety in industrial environment for stationary robot arms and also mobile robots that are stable on their wheels, we consider it safe when the robot doesn't move anymore, assuming that the human is not already between the robot and the wall in this moment. But the safety system would have failed if that would be the case. So the general aspiration of functional safety in the industrial context is to really ensure safety. So basically always make sure that when things go wrong, they don't go wrong, so to say. That isn't the case for a couple of other products. So there are a couple of systems where there is no such a universal safe state. For example, cars, especially autonomous cars. Considering the motorway, especially a German motorway on the left lane, it's not safe to stop that autonomous car because, basically the ones behind you, they might drive very fast and hit you. Same for the plane. It's probably not a good idea to stop a plane in mid-air travel, very obviously, because then it does exactly that, what we don't want it to do, which is to fall from the sky. And there is another product that has a similar problem. Stopping it doesn't make it safe. I'll elaborate on that in a moment. So the general target cannot be to ensure safety under all circumstances anymore. Functional safety becomes a support to reduce the accidents frequency and to reduce the accidents effect, basically. So making the system safer and not under all circumstances safe. So we will need to understand that the humanoid is probably a category of these products that cannot be made ultimately safe. Okay, so but why is it not a good idea to stop a robot? So here are a couple of things that stopped humanoids do. I think I'm not breaking news with showing this video. It's a very famous one on YouTube. It's DARPA Robotics Challenge back in 2015. A compilation of all the robots falling over, and they were falling over a lot. Yeah, so so let me introduce you to the state-of-the-art humanoid safety system. It looks like that. That's actually here. I took the photo yesterday. So, but wherever there is a humanoid, there is this crane, right? Because that's the only way today to make them safe from falling. Obviously, with humanoids weighing like above 50 kilograms, it's a source of danger, but I'll elaborate on that in a moment as well. Now, there's another dimension of safety risk when it comes to AI-controlled robots in general, not only humanoids, but as humanoids are now basically being propelled by the advancements in AI, simplifying the complexity of the kinematics for the first time, making it possible to make use out of these complex kinematics. Of course, AI control is of central concern. I mean, what's the difference? A traditional software stack is deterministic, right? A human wrote the code. Of course, we've got sensory events and stuff like this, but the code always does if this, then that, so to say. So we can consider everything that is happening during the runtime, during the development, basically what will happen during the runtime already during the development time. And then we can also compare what the robot is doing versus what we're expecting the robot to do, and in case it's deviating, we can stop it. So with deterministic traditional software, non-AI software, it's much easier to ensure safety on a behavioral level. Now with vision language action models and basically end-to-end AI systems, so video and language in, controls out, this is changing. It's widely undeterministic what this system will do. Not only in hallucinations, but also in general use. We cannot make sure that the robot will bring the apple when we're asking it to bring something healthy from the kitchen. It could also rather bring a knife and put it into us because robot thinks it's a good idea for the human. It's maybe healthy for the human, right? So how to make sure? And I mean, Generally, why is this dangerous? Another slide. Yeah, so this is from the Matrix, this precedent case where B166ER became famous by killing his owner because he was afraid that he will be turned off and decided it's safer for himself to kill its owner, which became the precedent case. It basically started the war between the machines and the humans. But again, why is AI actually a problem in terms of the functional safety and especially the certification of the software and the system? So again, we want to make sure that things don't go wrong when things go wrong. That's basically the essence of functional safety. So yeah, for the plane, we want to make sure that it's always going this way and never this way. And how do we do that? By first, of course, analyzing the risks, and then once we design the system that should control this product and implement basically all the features which are required to make it safe, we are performing failure mode effect analysis, basically take a close look to the system, what could go wrong and what are we doing about it. And then we're going into a V&V based development process or V-model based development process, so where all the requirements and the verification of the later implementation is linked and looped, so to say, which is fully traceable. So yeah, we perform a fail-safe design from the ground up, and then we certify it by having a third party usually examine completely traceable solutions from the beginning to the end for each given failure mode. So, and that is not possible for end-to-end AI systems because you basically cannot trace what is happening in that black box of a neural network. The only way to certify this is to perform a statistical proof of the reliability of that system and not change the training anymore. So learning systems, or basically systems that are AI-based and they learn during operation, they generally cannot be safety certified, at least with given approaches for certification today. And yeah, this can be quite tedious because you need to basically prove in many cases that it doesn't go wrong in order to create the statistics. Okay, so but what are really these sources of risk for humanoids in a nutshell again? So first of all, the same as it is the case for industrial robots, motion. Yeah, the humanoids, they move, they can hit humans, they can hit humans in a very harmful way, and we need to deal with that. The source of this danger of instability is actually the weight of the robot. Some robot designers trying to make their robots extremely light, but even if the humanoid is just 30 kilograms heavy, once it falls on a newborn or a cat or whatever other pet, it's probably not a good idea still. So it's probably still dangerous. So reducing the weight is not the only thing. It still remains a source of risk. Of course, depending on the use case. And then last but not least, as said, the behavior. That's the third main source of risk for any AI-controlled robot and any humanoid with that, basically. So what are we doing about this? Let's take a look into motion first. So what you see on the left-hand side is always now basically these sources of risk in a bit more an elaborate way, plus the failure modes that could occur within the system. And on the right-hand side, what can we do about it? So first of all, separation monitoring and human detection in the humanoid use case now. It's important basically to understand what is a human, what is not a human, in order to understand what do we need to limit motion, for example, towards. If you would do this for every object in the room, basically the robot would be quite limited in terms of its utility, so to say. Then situational operational space limitation. So that basically where, depending on what's the environment, what is the given action, we're limiting dynamically the operation space. Right. So if a human is here, we're basically putting an invisible envelope to the safe position limiting system and make sure that the robot is not moving out of this envelope. And yeah, situational safe range is basically based on a predictive approach for safe motion, where we are kind of not hardly limiting the operation space, but we're allowing for a certain dynamic range of motion, just to basically improve the duty cycle and the usability of the robot. So this is all state-of-the-art safe motion technology, which is not extremely common in industry, but which you can find in industry in advanced collaborative robot systems, for example, and it's clearly possible to be certified with Synapticon drives, for example. But it can limit the usability of the robot quite a bit, right? If you're limiting the operation space, how would you perform elderly care, for example? So when we need to kind of, help the human stand up from bed, for example, we need to do this with quite some force, right? So limiting the motion towards the human is not bringing or improving safety in that use case. So we need more than that. Now, in terms of stability, again, the more detailed risks, the failure modes, and what can we do about it. Also here again, separation monitoring and human detection is key, because in order to determine how we might want to fall more safely, it's a good idea to know where the human is, right? Because how do you want to fall more safely without knowing where actually the object that is endangered actually is. So, and then what do we do? It's about full body contraction and performing actions that are improving the safety of falling. And that is a first time in industrial functional safety that we're now performing actions in the case of a dangerous situation. Again, so far we've been only stopping, we've been only limiting the operation space or the force or the speed. Now we suddenly need to perform actions to fall more safely. So we need to basically parameterize the drives of the legs, for example, in order to fall in a certain way. And that's a first to industrial functional safety, if we consider a humanoid basically a sequel to the industrial robot world. Again, situational safe range here also helps to cover a broader scope. So it's unlike any established industrial safety and safe motion approach. Basically just what I said. Should have put these bullets out earlier. So the achievable safety rating of this is still unclear. We're working with several companies implementing such features now and basically working towards a SIL 2 rating, and that appears to be possible, but we still need to get there. So there's a path for that, and we're actively pursuing this. Now, basically, the most fancy level is behavioral safety part. Here again, some more detailed risk cases, the failure modes, and what do we do. You might have guessed, separation monitoring and human detection is again key, because otherwise we basically would observe too much of the environment. And then it's about supervising the robot's actions. So really looking at what does the robot do and interpreting these actions and determining is it safe for the human or not what the robot is doing. And in case it's not safe, which means, for example, like in this illustration, that the robot is walking towards the human with a knife, it's probably a better idea to stop the robot. So something is not right, at least it's not what we want the robot to do. And that is, again, unlike any established functional safety approach, with one little exception in autonomous driving. We've probably got a similar situation, but much more specific. One hand side more narrow, on the other hand side more difficult, because we need to react very, very fast. In a humanoid robot, we've got more time to apply such technology and to basically examine the behavior and then to react. Things don't happen so fast as like a car on the motorway, for example. We need to certify this based on success statistics, assuming that we can get there with an AI system that doesn't learn during operation. But even without that, even without certification, such a system practically improves the safety of the robot, and therefore is a great support for manufacturers in order to avoid bad news about their products, I suppose. So there's an evolution taking place now in functional safety. Let's take a look at different layers, basically, of functional safety in the robotics context, basically. So basic safety is the emergency off button, safely disengaging the drives, safely pulling a brake. This is all done with hard circuitry, which is then just safety certified based on tracing the circuit and redundancies and so on, and putting a stamp on it. Quite simple. Then again, state-of-the-art in industrial safety, now safe motion, safely monitoring the motion parameters. That is done based on safety-rated sensors or redundancy and software. Therefore, the redundant processors on the image before. Now, as we move to the new level, which is safe behavior, so where we want to do things like safe situational function limitation or safe behavior supervision, there is now the level where AI comes into play. So again, we need sensors in redundancy and diversity or with a safety rating, and then we've got safety software, which is AI-based, because with what technology otherwise would you want to interpret a universally intelligent robot application? These three levels are not to be distinguished, or are to be distinguished with the SIL levels, so not that anybody thinks I'm referring to SIL 1, 2, 3, so these are the safety integrity levels that generally describe the rating of the safety system. That's not meant by this here, just to make sure nobody gets that wrong. Now, the diagram from before about the general approach to make a system more safe. Now, how does that look like on the higher levels? So we've got the drive below, again, where motor and brake are connected through some safety circuitry to a non-safe servo drive, being monitored by a single-axis safe motion monitor that uses a safety-rated sensor, or again, redundancy and diversity on the sensor side as well. We do the same then on the multi-axis level. Yeah, so this is already state-of-the-art safe motion again, that we're not only doing this on the single axis, but we're also safely monitoring the transformations and the kinematics. So we've got a non-safe multi-axis motion controller, and we've got a safe multi-axis safety monitor. And exactly the same structure also comes into play in the third level, where we've got the robot software stack, for example, based on ROS or whatever, VLM or VLA-based robot application. We're putting an AI instance next to that to monitor the robot's non-safe AI. And we're utilizing non-safe and safe sensors for that. Now, this is again an overview about all the things that we can do in order to tackle these risks. Motion, weight, or you could call it stability, and behavior. Safe motion, predictive safe motion, and then there comes basically three aspects which are passive, kind of related to the robot structure itself. So making the robot's mechanical design already more safe than it would be if we don't consider these aspects. Low inertia actuation, so using tendon drives, for example, versus classical industrial style actuators because of much lower inertia. So basically, yeah, I think Bernd was talking about this when presenting 1X, because they're strongly following this philosophy, and a couple of others too. Then lightweight design, of course, making a lighter robot generally makes it safer, but as I said, probably not ultimately safe still. And then avoiding legs is a very good approach to avoid instability. But again, yeah, ultimately we want to have universal humanoids and they should have legs. So yeah, we need other areas to tackle this with. Now, at Synapticon, we're focusing obviously on these control system aspects, where then active contraction and behavioral supervision comes into play, and of course the safe motion system. And for this, we built Positron, the first platform to cover all these three layers of advanced AI-controlled robot safety. So bottom layer is multi-axis safe motion, of course, building on safety-rated drives. second level, safe human detection, and the third level is the AI behavioral safety. Let's go through these levels in more detail. Now, looking into the market of safety controllers for safe motion, the most advanced device that you could find in the market before positron was basically a DIN rail safety controller that could monitor maybe 10 axes and compute forward kinematics for 6 axes, and then that was it. But also in industry, you didn't need more than that. Now, when we're talking about 24 degrees degrees of freedom and more in a humanoid, we need more resources for that. And positron is the first safety controller that comes with plenty of resources and with the respective safety rating to safely monitor more than 50 axes and do advanced transformations, also inverse kinematics of up to 7 axes and several instances of that. So basically, no resource limitations, and it's the first time that such a compute platform is safety rated for SIL2, and of course the corresponding software foundation as well, to bring safe motion to humanoids for the first time. Now, safe human detection. Here basically we're leveraging safety certified separation monitoring and general obstacle detection. So basically safely knowing, okay, what is an obstacle in the environment, first of all, and then classifying which of these obstacles is a human. And for this we're using basically a redundant and diverse camera setup and a non-safe human detection next to a AI-based, a safety-rated non-AI-based human detection next to an AI-based human detection, and by this redundancy and diversity reach a safety rating again of SIL2 PLD. And yeah, that's some footage from that system working. Then on the third level, behavioral safety, we are leveraging multimodal foundation models, which are pre-trained with internet data actually. You can try yourself and ask ChatGPT when you give it an image if that situation that is on the image is dangerous for a human or not. It will give quite good results. Now the problem is running a GPT-4o or Gemini on an embedded system, and both of them, and probably 4 instances of them, in at least every second is a problem, right? So we're basically into optimizing these models and the execution in order to do this at a high frequency and in a given redundancy and diversity to be safety rateable. Post-training needs to be applied for more limited situations. So basically the examples which are here in the pictures, looking at the situation from apart, that's comparably easy and can be covered by internet data. So basically all different kinds of things that can be found in the internet and being labeled, so to say, what is dangerous and what is not. But when we've got a situation where the robot is, for example, cutting a carrot or installing a rack into a computer into a rack, we need to detect a human limb coming into the view, which is then going back to the safe human detection actually, but it's part of this one. Basically also need to throw the criticality level of the situation. Now again, this is contributing actively to the safety of the robot, because once we have such a system in place, the robot is obviously much safer than if we don't have it, even though that we can't so easily safety rate it today. But we're working towards this, adopting the AI certification path with non-learning AI. That is commonly a concept that is existing in functional safety. Now, positron, together with our motion controller motor cortex, gives robot designers basically all the infrastructure that they need to safely to build physical representations of their AI, so to say, so to create embodiment for their AI and to make these robots safe. So yeah, your robot software stack, be it VLM-based or whatever discrete ROS-based software, goes on top of the motion controller, real-time motion controller, and these safety instances. That is hardware. I'll skip that through. And yeah, as I mentioned, if you're building a robot and you want to do this quickly, and you've got performance targets, and yeah, it shall be basically mass producible in the end. It might be a good idea to check with Synapticon and see what ingredients we have to offer so that you can do this real quick and yeah, basically with a great result. And of course for the safety system as well. So we're a full stack provider of all the infrastructure for motion control for robots and for functional safety of robots. And we're actively helping our customers to realize systems with our business unit Synapticon Intelligence. I think looking at the time, I will probably not go through my summary, but thank you for your attention, and I will take some questions if that is still possible.
If anyone has one question, we could probably make one question work.
So the SoC you have on your is that your own IP or is that something that you're buying off the shelf?
We're using Intel and ARM processors. So we've got an Intel-based hardware and an ARM-based hardware for different use cases. The ARM-based one is for safe motion only, and the Intel-based one once the AI safety comes into place for the safe human detection and the AI behavioral safety. And that's a particular Intel chipset that provides basically a certification path. And then on the software level, works with a hypervisor and the like to be safety rateable. And then on top of that sits our software stack that is also pre-certified to SIL 2. Yeah, thank you.
Okay, so our final speaker of this evening is David Hansen, who is, I'm told, appearing remotely. He's in Hong Kong, but he should appear here right after I introduce him. Hansen Robotics, of course, was applying AI to robots for human interaction very early with Sophia, who you're probably all familiar with. And the thing I would say about Sophia is that it was arguably the first embodied AI system to be really highly exposed to the public. And that came with a lot of complications, and I'm sure that that was a very unique experience for David and for Hansen Robotics. And so that's something that we can all certainly learn from, and I hope that he will talk about that today. So if we can make David appear somehow.
My voice can appear. Hello, everybody.